Let's write a few more theorem and reminders for some calculations. And then today, while we are talking, I will talk a little bit about computational complexity and the number of operations we need to in order to solve some system of equations. But those information are kind of like extra information. You are not in general responsible for that, but it's for computer scientists it's important to know. Here, there are some cool inverses that you might like. To know them. And in all of them, A belongs to R n by n, B belongs to R n by m, C belongs to R m by n, and D belongs to R m by n. So you can guess that we will have lots of maybe block matrices, so on, to proceed. The first thing that we write is a very famous, it has a very long name, it's called Sherman Morrison Woodbury formula. And it is A plus BDC inverse is A inverse minus A inverse B, D inverse plus CA inverse B inverse CA inverse. Second one is if we have such a block matrix, this matrix inverse is this one, is this one, and similarly this matrix inverse is this. Third one is we have another block matrix, and this one's inverse is itself. in order to prove the number 2 and number 3, we can use the number 4 and number 5. A, B, 0, D inverse is A inverse 0 minus A inverse B, D inverse, D inverse. So in order to prove number 2, you can use this formula. Instead of I and D, if you A and D, if you put I, then you see that I inverse is I inverse is I, so it's I, B, I, which is B. So we are getting I 0 minus B. And the fifth one, A 0 C D inverse, which is A inverse minus D inverse C A inverse 0 D inverse. Again, for proving number 3, if here instead of A and D you put I, this part, we will get the other part. For proving number 3, again you can use these two, but instead of D, you will put minus I. I plus BC, C, B, I, inverse is I minus B minus C, I plus CB. And the 7th formula, we had it before for A, B, C, D. Inverse, it is A inverse plus A inverse B E C A inverse minus A inverse B E minus E C A inverse, and E, where E is equal to D minus C A inverse B inverse, which is called sure complement of A. If you remember, we had a sure complement of D also. Do you remember this formula from the early lectures of this class? If you remember, we used to say that this is also, we can write it as A, B, C, D inverse as F minus D, C, D inverse CF, D inverse plus D inverse CF, D, D inverse minus F, B, D inverse, where F is A minus B, D inverse C inverse. And we said that this term is sure complement of D. Now, why we need to, in general, know about the block matrices is that sometimes the matrix that we have is not a square matrix. And then we have to go to the difficulty of pseudo-inverse. Whereas maybe we can convert it into a square matrix, or let's say a square matrix, a vector, and then a number. So it can ease the process a lot. It can ease the process a lot. Even for example, if you want to calculate the inverse of a 4x4 matrix, you can say that a 4x4 matrix is actually a block of 2x2 matrices, where you can calculate the inverse of 2x2. In other words, this calculation will become very easy. You have the 2x2 matrices to multiply. Or even you can use this formula in order to calculate the inverse of a 2x2 matrix. Because a 2x2 matrix is the block matrix of 1x1 elements, right? Because for a single number, what is the inverse? It's just reciprocal of that number. Just reciprocal of that number. Of course, if the number is not zero. In more friendly form, we can solve the system of equation ax is equal to b using the following methods. We know that we can solve a system. Well, one of the ways that numerical methods like the Gauss-Jordan, right? In order to solve it. But there exist some other methodologies that we can use in order to solve such a system. So up to now we have seen how a system has a unique solution or has a solution, so we can check those things. But in case that it has, then we can actually use several methods in order to do it. And these methods are: 1, LU factorization. I will tell you about each of them in a minute, but let's first write them. Cholesky factorization. QR factorization, and definitely singular value decomposition. And we want to focus a little bit before we finish today's lecture, talk about the LU factorization or LU decomposition. Some places they call it LUD, lower upper diagonal decomposition, and we will tell you what they are. And then we will talk about also Cholesky factorization, which is very similar to the LU factorization, but in here we are dealing with a specific type of matrices. LU factorization decomposes the given matrix A into multiplication of two matrices, which one is lower triangular matrix and other one is upper triangular matrix. Sometimes we do this LU decomposition in the form. You know what is the lower triangular and upper triangular, right? Lower triangular means that if you have a matrix, we have the numbers in here in lower than the main diagonal, and what is upper the triangle, the diagonal is 0, and in the upper triangular matrix we have the numbers in the upper triangular, and we have definitely 0 in here. Look, it doesn't mean that we cannot have 0 in here. This means that definitely we have 0 in here. In other words, a diagonal like a singular matrix can be considered as upper triangular or lower triangular. Well, what sometimes we do, and we call it LUD, is we make sure the elements on the main diagonal are 1, and we define a diagonal matrix which has zeros anywhere apart from the main diagonal, and the elements which supposed to make the main diagonal will be there, right? So this is one way of solving a system of equation. Let's see how it does it. So we have AX is equal to B, and by using the LU factorization, instead of A, I can have the two matrices of LU. So I will write LUX is equal to B. Now I can call this part to be Y, so I have two systems of equation now. One is that Ly is equal to B, and the other one is that Y is equal to UX. Now, why this is better, converting one system of equation into two systems of equation? Because let's consider this one. Let's consider this one. What is the L? It is L11, lots of zeros, right? And then L21, L22, lots of zeros, and it continues like this, right? And then we multiply by Y1 till Yn equal to B1 till Bn. The first thing is that we know what is Y1. For the second multiplication, we know Y1, so the only thing that we need to calculate is Y2. So it's easy to find the results. And as we go to the next equation, we already know the previous unknowns. So same thing happens when we come to the upper triangular ones. And let's say this is U11, U1n, and we come to UNN. Now this time, x1 to xn, y1 to yn. This time, the last equation tells us what is the last unknown. The one before last, we already know the last one, so we can calculate the previous one. So it's very easy to find out what are the values of unknowns. Of course, we are increasing the number of process. So let's see how many operations we need in order to solve such system. Again, numerically doing it, I tell you that there is a command in MATLAB, I will write it down, that can do this LU decomposition for you. Number of operations for LU factorization is approximately 2/3 n cubed, and for solving the above, we erased it, the above new sets of equations, we need 2 to the power n square flops, floating point operations. So we are increasing the number of process and flops, but we guarantee that we easily get the results. So this is one way of doing the solving the system of equation. And in MATLAB, you may use LU in order to calculate LUD. If A is positive definite, then we can use Cholesky factorization which is this. Ax is equal to b. Instead of A, we write it as L transpose. In other words, we can have a lower triangular matrix multiplied by its transpose, which is giving us A. So previously we had to calculate two matrices. But if it is a positive definite matrix, we need only L. The U will be just the transpose of L. So then, we said that L transpose X is equal to B. So we have two sets of equations. One is Ly is equal to B, and the other one is L transpose X is equal to Y. And the number of operations what do we expect about the number of operations? In the LU factorization, we had about 2/3 of n cubed. Should be higher or lower?
1/3, because transpose is easy.
Yeah, it will be less, but it's actually 1/3 n cubed plus 2n squared. Because this is an approximation. So if A is positive definite, so question was that what is a positive definite? What is a positive definite matrix? How do I understand A is a positive definite?
We don't have zero singular values or negative.
What is the general definition of?
We assume that all the elements are greater than or equal to 0.
No, I mean we have to check that if the singular values are non-zero, but in general, what is the algebraic definition of positive definite.
A transpose A to be something like that.
A is positive definite if it is symmetric and X transpose AX is greater than 0 if X is not 0, and X transpose AX is equal to 0 if X is equal to 0 for any X. And we know that we have also another definition which is called positive semi-definite. Do you remember what is positive semi-definite? Positive semi-definite if it is symmetric, if X is not 0, this operation can be greater or equal than 0. Prove that A is positive definite and the A is 9665. Use the definition and prove that A is positive definite. Anders, how do we do that?
I assume to take some vectors of x.
So which vector do you take?
One of those should be a zero vector, and another one should be a non-zero vector.
I mean, what is a zero vector? Give me an example of a zero vector.
For example, 0, 0, 0.
0, 0, 0. Why 3 zeros?
Well, 0, 0 in this particular.
Yeah, okay. And non-zero one?
I would take, for example, 1, 1.
Why do you take y1? What will happen if it is minus 1 and 1?
I also intended to try that out,
What
but
about 5 and 12?
I believe that should be non-zero.
So why don't you take 5 and 12? I mean, maybe 1 and 1 or minus 1 and 1 are special cases.
Valid point. I do not.
So Ike, in case of 0, is 0, 0, we understand. What about the non-zero one? What do we have to take? You saw what was the problem with the Andreas? He was taking an example and wanted to prove with an example. You cannot prove with an example. You can disprove with an example, but with 1 million, 1 billion examples, you cannot prove something. So, can you tell me that, what is the vector x that we have to take? Like if you want to prove it, how do you prove it? I could tell me. I mean, you are proving it, right?
Yeah, I was trying to.
Okay, I mean, we have to take a vector x. What vector do you take?
X1 and X2.
No, I.
So you take a non-zero vector, so
Yeah, like what?
any arbitrary vector.
Any arbitrary numbers, like a and b.
Yeah.
A and b. Okay, please proceed. Andreas, you wanted to say something?
I
Yeah,
was
okay.
going to do it.
Look, I'm not proving it, but a very important comment. If you want to prove something, you may make some assumption and do it for one example or two examples. But you cannot say that now we can you cannot write a statement like this. Now we can generalize it and it is done. If you want to use the sentence now we generalize it, you have to prove how you are generalizing it. So the best is that we just simply start from scratch by having it arbitrary values, arbitrary sizes, and then go ahead. Of course here the size is fixed, because if this is 2 by 2, we understand that the size of x Laura, did you do that?
Yes, but I can't get rid of the cross components where x1 and x2 are in.
So let's see. X is, what is the size of x?
2 by 1.
2 by 1. So let's say it's x1 and x2, right? So x transpose AX is x1, x2, 9, 6, 6, 5, x1, x2. So this multiplication gives us 9x1 plus 6x2 and 6x1 plus 5x2 multiplied by x1 and x2, right? Correct me if I'm wrong. And the result of the multiplication is 9x1 squared plus 6x1 x2 plus 6x1 squared plus, oh, I missed one here, plus 9x1 x2 plus 6x2 squared plus 6. No, I'm doing it wrong. I cannot multiply two matrices. This multiply by this plus 6x1 x2 plus 5x2 squared. So it will be 9. Now, okay, we can actually do a little bit of cool stuff. What is this? How can I decompose it? 9x1 squared plus 12x1 x2 plus 5x2 squared. Look, I write it as 9x1 squared plus 12x1 x2 plus 4x2 squared plus x2 squared. Let's see, this is 3 multiplied by 2, so I can write it that this is 3x1 plus 2x2 squared plus x2 squared. Am I right? Now, we know that if, and this is equal to 0 if x is 0, right? Because if x1 and x2 all are zeros, the result is 0. If x is not 0, it can be negative value, it can be any value except 0. We know that this term is positive. This term is positive, right? Because it's a square, Now, can you tell me that if I am calculating, if I'm adding a positive number by a positive number, it will be? Look, there is one more